Hello everyone. Today I'm going to show you how to model a elastic plastic beam. For example, with steel material, as we know, steel is linearly elastic until the yield point, and after that, we assume a um, linear um, plastic region for modeling purposes, unless we have the test data to model it exactly. The stress strain response from um, for steel. So we don't have the test result. So what we can do is we can assume the steel to behave as linearly elastic and linearly plastic. So it's like bilinear elastic plastic material. So to do that, let me discuss where we stopped in last class with the linear elastic beam. So we had this type of material properties where the stress was increasing linearly elastically with a strain. Okay, as long as there is displacement or deflection, the strain will increase and the stress will increase accordingly in a linear fashion. And we have seen the force displacement response like this one in our last class. I forgot to compare the displacement as we have conventionally used formula. We can use them to calculate the deflection of the beam, and I calculated manually. The deflection was 0.036 inch, and from the first displacement response of the beam, linear elastic beam, we got around 0.043 inch of displacement. So the difference between these two, 0.036 calculated and 0.043 from the ABAQUS result can be attributed to the finite element methods and the uh, solid element we consider in the traditional or conventional mechanics formula. So ABAQUS is a finite element analysis method, which considers the beam as segments. For example, we had to mesh our structure, right? But in the classical mechanics, we assume it as a rigid body. So that can be the source of discontent between the calculated and ABAQUS displacement here. But anyway, it's not significantly different. As you can see, it's 0.043 inch and 0.036 inch. So it's not significantly different if we compare it in like if we go at a higher displacement, I believe it will be really comparable. So again, coming back to our uh, elastic plastic material definition. So I want to draw here that if we model the material as elastic plastic, we can actually the steel stress strain response is linearly, it goes linearly up like this, and then at yield point it goes like this, and then it continues like this. So we see some hardening too. So as I said, as long as we don't have the test results from a river tensile test, we can model this behavior using a linear and then linear elastic and linear plastic, perfectly plastic, or sometimes we use a um, increasing plastic displacement. Okay, but for modeling purposes here I am using a linearly, like up at yield point it will continue as the yield stress as long as it does not fail, and we know it still can fail at 28% of elongation, depending on the grade. If you have higher grade, still it will fail at maybe even 8% or 10% strain. Okay, so this failure strain where the steel will just tear up, it will be like point 0.2 or 0.1, whatever. So I think I assumed as 0.2, 20% strain. So this will be our elastic plastic region. Once an element hits this elastic strain, say depending on the modulus of elasticity and the stress here. So if it's a 60 grade steel, that means my yield stress is 60 KSI, right? In US terms. So in MPa, it will be 415 megapascal, I believe. So if you divide this 60 KSI with the modulus of elasticity of steel, which is 29,000 KSI, so you will get the yield strain as, I believe, 0.00207. Okay. So as soon as the material reaches this strain, after that it will assume a constant stress of 60 ksi until it reaches the failure strain. Okay. So let me go to the model. I request you to watch the previous lecture I gave on linear elastic beam. So that's my channel. You can come here, Civil Engineering Lectures by Dr. Kabir Hossain, and you can find this one, uh, ABAQUS linear elastic beam analysis and uh, comparing the stress displacement with beam formulas. So if you watch this one, you will know how to model beam and see the results. Ultimately, I'll just show how we can incorporate the plasticity material properties to the elastic beam and run it and see the results. Okay. So you create the part the same way I have shown in my first lecture. You come to the property module. In the property module, you open this property manager, and we have a steel material which is defined as linearly elastic. We click on the edit menu and it shows this behavior. So we define the density. I think I made a mistake here also. After the lecture, I remembered it. We inserted this mass density in pound per cubic feet, but since we are using FPS unit, this should be in pound per cubic inch. So as long as it's a static, general static analysis, the mass density does not matter a lot, but for dynamic analysis, it can matter. So that's why we didn't see any effect on our results, although we had a like wrong mass density. Okay, but we should always use the correct value. So 490 pound per cubic feet, we need to insert it in pound per cubic inch. So we need to divide this value by 12 cube. Okay, so it will be 0.28 pound per cubic inch. Okay, so that's one. Then we go to elastic. We have the Young modulus as 29 million psi and Poisson ratio 0.3. These two are needed for elastic material. But for plasticity, we go to mechanical, then plasticity, and then plastic. So we have different types of plasticity, but we do not use them for perfectly plastic or bilinear elastic plastic material. You can just use this plastic. Okay. So it's asking for yield stress. What it's asking is basically it's asking this point and this point. You can have multiple point definitions since it's a linear line. I don't want that. I'll just insert this value corresponding plastic stress and this value and failure stress. Okay. So this is corresponding plastic stress means total stress sub from that's the stress which can be calculated by subtracting the elastic stress from the total stress. So that's total stress. You need to subtract 0.00207 to get the plastic stress, which is not a lot. So I just use this total strain as a plastic strain. Okay. So here in this material model, we just insert since it's 60 grade steel, so the yield stress is 60 psi. That means 60,000 psi, and the strain is 0. This is the yield point. Okay, then I need another row. If you click enter, it will create another row. um, I'm modeling it without any like a stress increase. So I'm modeling with just a by uh, uh, linear like horizontal line after yielding without any stress increase that we typically see in steel. And I will put this stress as a point, sorry, this strain as 20% or 0.2. As I said, the plastic strain is total strain minus elastic strain, but the elastic strain 0.00207 is very small. So compared to the failure strain, the elastic strain is almost nothing. That's why I'm using 0.2. Okay, so once you click on this one, that's the only change you need to model this beam as elastic plastic material. So we click on dismiss and then we submit the job. So before we do that, we want to probably click on save and save it as a different file. We can do that. It will take some time because we have inserted the plasticity in our material model. We have nonlinear geometry also. So if it deforms a lot, it will take a lot of time and probably it will abort the job without fully completing. So I will not wait for its results, but I have done some analysis on another beam, and I will show the results from here. So as you can see, this is a beam that I modeled with in megapascal, like Newton millimeter unit. So do not be confused with the unit here, but my intent is to show you that we can model it and compare the results. I will show you my material property here. So we have plastic material. This is 60 grade steel, and it's 60 KSI is equivalent to 415 megapascal. Okay, so I have defined this material defined as elastic plastic, and I'll just show you the results. So let's go to visualization, and we want to see the longitudinal stress. Say, I want you to watch it carefully as I go through it. I want you to see the material stress development or evolution in this beam. Okay, keep an eye on the stress involvement. So this is the uniformly distributed load, and I loaded with like 4,100 kip per linear feet. That's a significantly high load, although this beam is so significant too. That's 12 inch by 20 inch. It's still rectangular section that can carry a lot of force, right? But I overloaded it basically. But I want you to see the stress evolution. So you can see till now the flexural compressive stress at top and flexural tensile stress at the bottom are exactly equal. Keep an eye on the stress value and also the contour movement. So as we are pushing with more load, more stress is increasing, and you can see it's propagating towards the end, and the tensile stress, which is, as you can see, the maximum tensile stress we had, the yield stress is 415 megapascal. Here we are seeing 420 megapascal. That's close, okay? The compressive stress is higher. At support region, you will see more compressive stress. That's actually here we are seeing. But I want you to see this region at the bottom and at the top. You can see the yielding is now propagating towards the bottom. So in rectangular beam, what we see, the stress in linear elastic distribution is like this. But as we keep pushing, the top fiber yields, then the lower fiber yields, then the lower fiber yields. It continues until the steel becomes perfectly plastic like this, right? So that's where the plastic hinge occur when the stress is perfectly plastic. Basically, this will not be like exactly like that. There will be a linear portion here, but this depth will be very less. And I want you to observe it here. So as you can see, the yielding is just propagating from the bottom and the top towards the mid depth of the beam. Okay, and also it's propagating towards the end of the beam from the mid span. And if we keep pushing, you will still see the neutral axis, the plastic stress is still increasing, and you can see the stress value is not increasing, but the region of yielding is increasing. Okay, and right before plastic hinge formation at the mid span, you can see probably the unyielded part of the beam is like 1 inch or so, and then in the very next step, the beam deflects a lot, and you can see all the elements above neutral axis at the mid-span especially has yielded, and also at the bottom it has yielded. We can see some extremely high compressive stress, but that's not here. It's at the support actually. You can see the blue region. So we see it there. But my point is, like, we from our steel design class, if you guys have seen my steel design lectures, I have shown from a book that how this steel beam behaves if we keep pushing. So this is the typical response as we have seen in our mechanics or steel design class. We can see it from ABAQUS too. Okay, so this is the typical steel material, but with linear elastic plastic material. And if for steel, we can just assume that way. But for concrete, definitely this mass deflection will not occur. Without any reinforcement, it will just break into two pieces. I will show that in a lecture. But if we reinforce it with, say, longitudinal steel rebar and shear rebar, we will have some resistance like this. But the concrete intention, it will crack, and at some point, if you overstress the concrete in compression, will crash too. So we'll cover those parts as well. But for now, just see the behavior of steel material. If you uh, want to see the failure of steel beam under flexure, this will be the typical failure behavior. So after seeing this stress or failure mechanism, if we keep pushing, now the force does not increase that much, but the displacement increase a lot. I also want to show you the displacement here. So I want to show the vertical displacement. As you can see, keep an eye. Zero, the red part is like close to zero stress, okay? So the beam is just deflecting, watch the values, and at some point, so right before plastic hinge formation, the displacement is like 23, 24 inch. At displacement, at plastic hinge formation, it's like it increased drastically to say maybe 300 or 200, 400 millimeter. Sorry, the previous one was 24 millimeter, but it has now increased to 400 millimeter. You see, right after plastic hinge formation, the beam still continues that load. So the stress is that is still there, but it deforms a lot because it cannot take any more force, but it can deform until it faces at extremely high strain, which is like 28% or 20% or 15%. Okay. So if you keep loading, it will not take more load, but it will deform a lot. As you have seen, this is extremely distorted, and the beam will not probably go there like that. It will fail if you really test it. Now I want you to see the force displacement response also. So in the previous video, I have shown how to extract the force displacement, force and displacement values, right? Let me show you again here. So we go to the field output option. We this is extract the vertical displacement at midpoint. We choose unique nodal, and then we pick a point from the view. So I'll just pick, let's go to the stress option and then pick a midpoint um, from here so that we can have our stress value. It looks like one of these points will be mid. So I'll select one point here and then get the displacement, okay? So save as, click on yes. We have this value already, so that's why, oh sorry, we haven't selected any point. It's showing that. You see, now we have selected and we can save it. Then we can go to for reaction force RF here, RF2. We want those values from node sets. We have created reference point 1, reference point 2, and associated those node area to this point, so we can save this data as well. So once we have it, we close this one and then we click on the XY data manager and we extract this data, okay? Click on edit, click here and then Control C and paste this data here. So that's how I did it. I also copied the reaction force RF1 at node 1 and RF RF2 at node 1 and RF2 at node 2. So in node 1 is the RP1, that means reference point 1 on left support. Node 2 is RP2, which is right support. So I extracted those values as well, like this, and then I copied them in Excel file. So I copied them here. I extracted the vertical displacement at midpoint of the beam in millimeter. I converted that in inch, and also the vertical displacement was downward. So I just used a negative sign to convert it into positive displacement so that we can show it in force displacement response, and displacement will be positive. Then I extracted the left support reaction and right support reaction in Newton. So I converted that Newton force into a total force in kip. And you can see here the force displacement response from the elastic plastic beam. So at yielding, right after yielding, the force does not increase, but the displacement increase linearly. Okay. But for the linear elastic beam, this is the force displacement response at up to that load. As we keep loading, it will keep going. And for the elastic plastic beam, that's we know from theory that after plastic hinge formation, it cannot take more load. In reality, still will take some more load, uh, because it has that strain hardening, and that increase in stress, but we are not assuming that, right? So we are modeling this with a linear property here after yielding, and we have seen similar force displacement response in from that analysis results too. So I think this is very important to understand the material behavior, especially the steel design. When you design a steel building, you can understand like how my beam or slab or column will fail, basically. Okay. So again, this beam was uniformly loaded over the whole span, but in next lecture, I want to show if we just apply a displacement load at the top, and then how this beam will behave. Okay. So we have so far 2 lectures covering uniformly distributed load over the whole span, with one with linear elastic material and another with elastic plastic material. The next one will be elastic material, maybe with uniform with a concentrated displacement loading. So in the lab, when we test a beam, say, we can apply load here or displacement here. Basically, we are applying load, but at a displacement control or a load control method. So we usually we apply displacement control load to see at what load it fails. If you just apply a certain load, it will not fail, right? But it's better to see at constant rate of increment of load than the other one. So I think I'll just stop this lecture here today. If you have any comments, let me know. We can discuss. Okay.